In 1928, a scientist came back from a 2-week vacation to a messy lab and one forgotten petri dish. That accident directly led to a discovery that has since saved an estimated several hundred million human lives. Welcome back to Breakthrough on Neuralfeed. We've covered the printing press, the light bulb, and the telephone. This week's invention wasn't really invented at all, in the traditional sense. It was discovered, almost entirely by accident. Penicillin. Let's get into it. Alexander Fleming, a Scottish bacteriologist working at St. Mary's Hospital in London, was researching Staphylococcus bacteria in 1928. Like many working scientists of his era, Fleming was reportedly somewhat notoriously untidy in his day-to-day laboratory habits. Before departing for a 2-week summer vacation, Fleming left several petri dishes containing active bacterial cultures sitting out on his lab bench, rather than carefully sterilizing and properly storing them away first, as more meticulous standard laboratory practice would have called for. Upon his return, Fleming noticed that one specific dish had become accidentally contaminated with a blue-green mold, almost certainly drifting in from a separate mold research laboratory located one floor below his own. Critically, Fleming noticed something else immediately around the area of mold contamination, a clear, distinct zone where the surrounding bacterial colonies had visibly failed to grow at all, in sharp contrast to the rest of the dish, which remained heavily and normally covered in dense bacterial growth. Most working scientists, faced with an obviously contaminated and now compromised experimental dish, would have simply discarded it without a second thought, exactly as standard sensible laboratory practice dictates. Fleming's particular genius, in this specific moment, was recognizing that this contamination might actually represent something genuinely significant and worth deeper investigation, rather than simply throwing the spoiled sample away. Fleming correctly identified the contaminating mold as a specific species of Penicillium, and he found that whatever specific substance it was naturally producing and actively secreting into its immediate surrounding environment was directly killing nearby bacteria. He named the substance penicillin. Here's the underlying mechanism, now well understood through decades of subsequent research. Penicillin specifically works by directly interfering with bacteria's ability to properly build and maintain their own protective cell walls. Bacterial cells continuously need to actively synthesize new cell wall material as they grow and divide. Penicillin specifically binds to and effectively blocks certain key bacterial enzymes that are essential for properly completing this cell wall construction process. Without a properly intact, structurally sound cell wall, bacteria become genuinely unable to withstand the internal osmotic pressure naturally generated within their own cells, and they ultimately rupture and die as a direct result. Critically, human cells don't have cell walls at all, only an outer cell membrane, which is structurally and chemically quite different. This specific structural distinction is precisely why penicillin can effectively and selectively kill many types of bacteria while remaining largely safe for human cells and tissue, making it genuinely usable as an effective medical treatment in the first place. Fleming published his initial findings in 1929, but his discovery received remarkably little immediate scientific attention or interest at the time. Fleming himself faced significant, genuine technical difficulty trying to isolate and meaningfully purify penicillin in sufficient quantity and stability to be reliably and safely used as an actual medical treatment. And he reportedly grew increasingly discouraged by these specific practical challenges over the following several years. It wasn't until 1939, a full decade later, that a dedicated team at Oxford University, led by Howard Florey and Ernst Chain, took up the considerable technical challenge of successfully purifying and meaningfully stabilizing penicillin in sufficient quantity for proper, rigorous testing. Their team successfully achieved the first documented, properly controlled test on a human patient in February 1941, and despite that specific patient ultimately dying after the team's initially limited penicillin supply ran out entirely partway through his necessary treatment course, the trial nonetheless clearly
clearly demonstrated the substance's genuine, dramatic clinical effectiveness against active bacterial infection. The Oxford team faced an immense, persistent practical challenge throughout. Penicillin was extraordinarily difficult to produce in any meaningful quantity using the laboratory methods and technology available at the time. Producing even a comparatively small amount sufficient for treating a single patient required cultivating and processing an enormous volume of mold.
With World War II actively underway and the urgent, obvious medical need for an effective treatment against deadly battlefield wound infections becoming increasingly clear, the British and American governments specifically prioritized solving penicillin's persistent mass production challenge as a genuine wartime priority. American pharmaceutical companies and government researchers, working in close, urgent collaboration, eventually identified a considerably more productive strain of Penicillium mold, and they specifically developed an improved deep tank fermentation process that dramatically increased overall production yield compared to earlier, far more limited surface culture growing methods. By 1944, penicillin production had successfully scaled to a level sufficient to treat the large majority of Allied soldiers wounded during the D-Day invasion of Normandy, a genuinely dramatic, transformative improvement from the desperately scarce, severely limited supply available just 3 years earlier in 1941. Penicillin is now widely credited with substantially reducing wartime deaths from previously routine bacterial infection, which had historically killed a significant proportion of wounded soldiers in essentially every major war fought throughout previous human history, even when the original combat wound itself was not immediately fatal. Remarkably, Fleming himself directly anticipated a serious problem with penicillin's long-term future effectiveness, well before it even became broadly available as a treatment. In his own 1945 Nobel Prize acceptance speech, he explicitly warned that bacteria could potentially evolve genuine resistance to penicillin if the drug were ever used carelessly or inappropriately, at insufficient doses, or for unnecessarily extended periods. His specific prescient warning proved entirely accurate. Bacteria reproduce extremely rapidly, and through the same fundamental process of natural selection and genetic mutation, any individual bacteria that happen to possess some degree of natural resistance to a given antibiotic will, through that resistance, survive treatment and continue reproducing, while the surrounding non-resistant bacteria are effectively eliminated by the same antibiotic. Over enough successive generations of this same general selective process, repeated across an enormous sustained scale of widespread antibiotic use, resistant bacterial strains can become genuinely common and dangerously difficult to treat with that same drug, sometimes within a relatively short number of years. Antibiotic resistance is now widely recognized as one of the most serious, pressing challenges in all of modern global medicine. The World Health Organization has specifically identified it as one of the top current threats to global public health, directly driven by a documented combination of overprescription in human medicine, routine large-scale use in livestock agriculture, and a genuinely slowing overall pace of new antibiotic drug development across the pharmaceutical industry in recent decades. A messy lab, a forgotten petri dish, a scientist who chose curiosity over simply discarding an obviously contaminated sample. A full decade of difficult technical work to make the discovery genuinely usable, and a wartime production race that helped save an enormous number of lives, alongside a warning, made at the very moment of triumph, about exactly how that same victory could eventually unravel. Next week on Neural Feed, we close out Breakthrough with an invention that began as a small, obscure Cold War research project and grew into something that now touches nearly every single human life on Earth: the Internet. Subscribe so you don't miss the finale. Drop a comment. Did you know Fleming himself warned about antibiotic resistance decades before it became a major global problem? See you next week.